So hello my colleagues, and I hope everyone is well. So I want to pick up here with regard to chapter 10 and another way of calculating annual returns. And this one is called the average annual return. And this is different than the returns the expected returns we calculated earlier. You notice there was a probability term there, a P. Notice here now, this is returns of an investment that's historical. So you see the words historical period. That means the probability is 100% because it happened already. Okay, and this is just the average of the realized returns for each year, right? So realized means it happened already, right? And it's with 100% probability, right? So that's 100% probability. So if this is the realized return of a security, then the average annual return over T years, or T periods we could even say, is just simply the sum divided by T. Now this was similar to what we saw before, except there was no probability term there, right? Because it was 100%. And now we're just taking and dividing it by the number of years, okay? So this is the average annual return of a security historically with known, probability, right? So the average annual return, this is the balancing point of the distribution. And so in this case, the probability of a return that occurs in a particular range is measured by the number of times the realized return falls in that range. So if the probability distribution of the return is the same over time, the average return provides an estimate. So this is just an estimate of the expected return, right? So we're basically getting an estimate of the expected return, right? And so here they are. You're doing it for the S&P 500, I guess for about 12 years or so. So the average return was 10%, right? Or 13 years divided by 13. And the average for T-bills was 1.2. So investors earned 1.18%, which is the difference between that guy and this guy, more on average holding the S&P. So this is why you don't really want to invest in treasury bills over the long haul. You want to invest in the stock market, right? So table 10.3 provides the average return for different investments, and here they are. And you can see small stocks return the most, right? Small stocks return the most, and T-bills the least because there was very little risk with those. So here is the variance and volatility of returns. So the variance, okay. Now we did the variance earlier. This time, this is the variance of known stocks already. So this is the variance estimate using realized returns, again with a probability of 1. All right. So you'll notice here, basically they take, subtract 1 from this number here, okay? And then it's just the sum of the difference, and this is the return minus the average return. So we estimate the standard deviation or volatility as the square root of the variance, right? So the standard deviation will just be the square root of this. So the math isn't really hard here. What you simply do is just take this difference, square it, add them all up for each year, and divide by 1 over T minus 1, where T is the number of periods, right? All right, so here's how they do the variance here. From table 10.2, you'll notice, again, here's the mean, right? The mean, they just keep subtracting it off of each return. They square it. They sum it up, divide by 1 over 12 in this case, right? 13 minus 1. And you basically get the variance of 0.029. And the volatility or standard deviation is the square root of that. So the square root of 0.029 is 0.17 or 17%. Okay, so that's all you really got to do to get the. So once you get the hard part of the variance, then you can simply just take the square root to get the volatility or the standard deviation. Now you'll notice that the returns the returns for small stocks was great, but now look at the volatility. You can't have your cake and eat it too, right? So you're going to get a lot of volatility with small stocks. Okay. All right, so now we got to look at some estimation error of what we're doing. So we're looking at past returns here to predict the future returns. And if you're going to use past returns to predict the future returns, there's a couple of problems. And they tell you right here. There's two difficulties with this approach, all right? We do not know what investors expect in the past. We can only observe the actual returns that were realized. Right? So in 2008, investors lost 37% investing in the S&P 500, and that was the year that the markets crashed, which is surely not what they expected at the beginning of the year, right? If we believe that investors are neither overly optimistic nor pessimistic on average, then over time, the average realized return should match the investor's expected return. And then here comes the second difficulty. The average return is just an estimate of the true expected return and is subject to estimation error. As we saw, that's just an estimate, right? So we're going to have an estimation error there. All right. So the standard error of the estimate of the expected return is given by this equation right here. So this basically standard deviation here, right? So this is the standard error, and that's shown as SD, right? And that's the average of the independent identical risks. And we have the standard deviation here of the individual risk, and we divide by the number of observations, okay? So this average return here should be within two standard errors of the true expected return, approximately two standard deviations, or 95% of the time, okay? So we can use the standard error to determine a reasonable range for the true expected value, right? And that's called a 95% confidence interval for the expected return. So the historical average return is plus or minus 2 times the standard error, okay? So you can kind of see what they're doing down here. The average return for the S&P was 12%. And they're just solving this equation right here, right? See it right here? So it's 12% plus or minus 2 times the standard error, which we get from this equation right here, which is 19.8%, right? Divided by 92. So this is 92 years of data here, right? So we get 92 years of data. And the volatility is 19.8%. So what we've got is a range of 12% plus or minus 4.1%. So with a 95% confidence interval, we can go from 7.9 to 16.1 average. Okay, this tells us the estimation of our error, that it's not truly 12%. So we just tack on and subtract and add the estimation portion. So even with 92 years of data, we cannot estimate the expected return of the S&P accurately. So you can see what we have to do is we had to basically take into account the error, 95% confidence interval for the error. All right, so here's the returns from the S&P for, I guess, 13 years again. What's the 95% confidence interval? So basically what they calculated previously was to be 10% with the volatility of 17. So the standard error of our estimate of the expected return is 17 divided by 13, square root of 13 readings. It's 4.7. So it's 10, which is right over here, right? Plus or minus 2 times 4.7, right? Or from 0.6 to 19.4%. So as this example shows, with only a few years of data, we cannot reliably estimate expected returns for stocks. So lo and behold, we now have another way of measuring a return. We already talked about the arithmetic average return. Now we got to talk about the compound annual return. And that's really the true number, okay? So we compute average annual returns by calculating an arithmetic average. An alternative is the compound annual return. And this is the compound annual growth rate, or CAGR, okay? Which is computed as the geometric average of the annual returns. So this gives you the geometric average of the annual returns. And this is not the arithmetic average. Now notice the difference here. We did the arithmetic average, now we're doing the geometric average. And the way we get that is we multiply each period, 1 plus each period. You notice how we're multiplying here? And then we take it to the 1 over t power minus 1. And this is equivalent to the internal rate of return. So the compound annual growth rate is the internal rate of the return of the project, of the investment over that period, right? So this is an important thing to know, the difference, okay? So this is the same thing as the final value of the initial investment to the 1 over t power minus 1. That's what you're seeing right here. This and this are equivalent, okay? So this and this gives you the internal rate of return. So the compound annual return for the S&P, for I guess whatever it was, 92 years or something here. They added up all the returns, right? And basically divided it by 100 and subtracted 1. This was the final value. This was the initial investment. And it was 10.04%. And you could get the same thing if you took the returns for each year. So if you invested in the S&P 500 over, I guess, 92 years, as we said here, that was equivalent to earning 10.04% per year over that time period. Similarly, the compound annual return for small stocks was 12.66, and again for T-bills was only 3.3. So in each case, the compound annual return is below the average annual return, shown in table 10.3. The average annual return basically shows it to be too high, right? So the compound annual return is really the actual return, and it should be average over compensates for your return. So if you have an investment that has an annual return of 20% one year and minus 20 the next year, the average annual return is 0, right? But the value of $1 invested after 2 years is what? 0.96, right? So an investor would have lost money, okay? So you can see the average annual return doesn't give you the same results that the compound annual growth rate does, right? So the logic implies that the compound annual return will always be below the average return, as we saw, and the difference grows with the volatility of the annual returns. Okay? So, anyway, that's good to know. So which is a better description of an investment's return? The compound annual return is a better description of the long-run historical performance of an investment, right? It gets more accurate. It describes the equivalent risk-free return that would be required to duplicate the investment's performance over the same time period. Okay? So conversely, then the arithmetic average return, we'll use that when we're just trying to estimate an investment's expected return over a future horizon based on its past performance. Okay, so they have different uses. So if we view past returns as independent draws from the same distribution, then the arithmetic average return provides an unbiased estimate of the true expected return. All right? All right. So if this is for looking at past returns, right? So if you go through this example, so the average value in 2 years will be $1, so that the expected annual and 2-year returns will both be 0, right? All right, so we'll pick up here next time. This is about 16 minutes long now.